In section 14.2, we're going to take a look at limits and continuity for these new functions. Functions where the input is a point in n space and the output is just a number. Okay. So, if I'm taking the limit, I'm using generic notation here. P is just a point in n space. That way I can use this notation whether we're talking about 2 space or 3 space. So as P approaches a specific point P naught, of f of P is L. L would of course be a number because f of P is the numeric output of the number. Okay. And what this means is sort of informally, as P, my arbitrary point, gets close to P naught, f of P gets close to L. Okay. Now I want to just talk a little bit about the different notation that we can use for limits of these new functions. And then we're going to talk about the formal definition of limit, which isn't something that we use an awful lot, but it's going to help us in understanding continuity for functions of multiple variables. Okay. So I'm going to just, as an example, suppose that I have a point P naught in 2 space, which is x naught, y naught. And everything that I'm about to generalize, to write using the components or the coordinates of the individual point would of course generalize to 3 space. There would just be a z value instead. Okay? So if this is my specific point, then an arbitrary point P would just be x, y. Obviously in 3 space an arbitrary point would be x, y, z. Okay. So I could write the limit as P approaches P naught of f of P, or I could write the limit as xy approaches x naught, y naught of f of xy. So I could write things in terms of their coordinates. I'll usually do this when I'm looking at a specific example, but I find this notation really helpful for talking about limits in general so that I don't have to say things twice. Here's what it means in 2 space when there's only an x and a y, and here's what it means in 3 space when there's a z value too. Okay? All right, it's also acceptable to write that it's the limit as x approaches x naught and y approaches y naught of f of xy. So you can write that the x and y, and of course in 3 space the z's, are individually approaching the components of that fixed point. I'm not a huge fan of this notation, but you'll sometimes see it, and there's nothing wrong with it. I think it's just a little bit easier to see that we're talking about that as an ordered pair when you write it as an ordered pair. Okay. It would also be okay to use vector notation. Okay. So I could say A is x naught, y naught, the position vector for this particular point. When I write it in parentheses like this, I'm thinking of it as a point. When I write it in brackets like that, I'm thinking of it as an arrow that would point from the origin to that point. And of course, graphically, I would represent it as that point. And then I could say x would be the position vector for my arbitrary point P. Okay. And then I could, if I wanted to, write this as the limit as x approaches A of f of x. Okay. Now, you'll notice that's treating the input as a vector. That's perfectly fine. I'm thinking of the input as being a point or a location that I have in 2 space or in 3 space, but it's totally fine for me to identify that point with its position vector. So we did that when we were working with vector functions. We can do that when we're working with functions of more than one variable. I generally think it's helpful to think of this as the input is a point, because what I'm really doing is I'm going to that location and attaching a height to that particular point, but it's perfectly acceptable to identify that point, that location, with its position vector. Okay, so that's all of the notation that we can use, and of course it can be appropriately modified if I happen to be in 3 space, and then I would just have 3 components. Okay. Now, this is sort of informal, because this just says as P gets close to P naught, f of p gets close to L. The formal definition of a limit has to formally define what's meant by closeness. Okay? And to do that, we introduce two variables, which are going to be our standards of closeness. One standard for how close the output gets to L, and one standard for how close the input gets to P naught. Now, this formal definition of a limit is an optional topic in 3A, so you may or may not have seen it before. Okay? I'm not going to go into a lot of detail about it. I am going to tell you what it is. You're not going to be responsible for formally using that definition, but we're going to use it together to understand continuity of some very specific functions, which will then allow us to understand continuity of all sorts of functions. Okay, so what we do is we introduce epsilon. And this is a positive variable establishing what I call a standard of closeness. For the output f of p, and the number that we're claiming is our limit. Okay, so the absolute value of f of p minus L, now these are just real numbers, so the absolute value of this difference is just the distance between f of p and L, and that would be on a number line. Okay, and we're going to require that this distance be smaller than epsilon. Okay, so our goal is going to be to show that we can make this smaller than epsilon, and we're specifically using a variable here, because if I used a specific number and I said I bet we can get within 1 unit of L, that doesn't mean we're getting arbitrarily close. But if for any positive value of epsilon, in other words, no matter how small I make epsilon, so no matter how close I want these two things to have to get to each other, I can force that to be true. That's going to mean that we're getting arbitrarily close. Okay, so that's how we're going to use our epsilon. That will be our standard of closeness for the outputs. Okay, and then our delta, that's a Greek number delta. Now, the triangle symbol is like a capital delta. So you've seen that before when you look at the slope of a line and you call it delta y over delta x. That's the capital letter. We're using the lowercase letter here. Okay. Now, this is also going to be a positive variable. And it's going to establish, again, what I call a standard of closeness for the input, P and P naught, to measure how close these points are getting to each other. Okay? And, of course, these are going to be points in n space. So I can't talk about the absolute value of their difference, but I can denote things one of two ways. dpp naught, or the magnitude of p naught p. And here it does not matter whether I do p naught p or pp naught. I create a vector that connects these 2 points, and then I take its magnitude. Either of these is a way of denoting the distance between P and P naught. So this notation we're familiar with. This is notation that I'm introducing now. Totally optional which notation you use when we're talking about distance. And there will be times throughout this chapter when we're talking about the distance between 2 points. I'm fine with you using either of these. This notation is not introduced in your textbook, but I find it helpful, particularly when we're more thinking of things as points rather than vectors, to not have to switch to vectors. But these mean exactly the same thing. They both mean the distance between P and P naught. Okay. So, we're going to introduce these variables, and here's how the formal definition of a limit works. Okay. So this is my informal definition of a limit. The formal definition says this: for every epsilon bigger than 0. Remember, epsilon was establishing the standard of closeness for how close my output f of p was going to get to L. So when I say for every positive number epsilon, that includes big numbers. But what I'm concerned about is that includes arbitrarily small numbers. So no matter how close I say I want the outputs to get, there is a delta bigger than 0. Okay. So for every standard of closeness I set for the outputs, I can find a corresponding standard of closeness for the inputs. So that if 0 is less than the distance between p naught is less than delta. Okay. I'm sorry, that shouldn't be a delta, that should be a d. And if you preferred to put the magnitude of p naught p or the magnitude of p naught here, that's totally fine. They all mean the distance between these points. So this says the distance is smaller than delta. So that says the points are close using delta as my standard of closeness. This part of the inequality says that the distance between p and p naught is not 0. So that p is not the point p naught. It's a different point. That's important when we talk about limits, because we often will take the limit as we approach a point that's not in the domain of the function. And if I allowed the distance between my point and the point that I'm approaching to be 0, then I'd only be allowed to take limits as we approach points that were in the domain. Okay. So this is saying it's okay if that's not in the domain. It's also okay if that is in the domain, but the function does something weird there. So when we're working with functions, just y equals f of x, if I have a function like so, at this point A is in the domain because there's a point there, but I don't consider that point when I'm taking the limit, because I say the limit is what I expect based on the nearby behavior. What happens when I get close to but not at A? So that's the same thing that's going on here. We're talking about getting close to a point but not concerned about what happens at that point. Okay, so if this is true, then the absolute value of f of p minus L, which remember is the distance between my function value and the limit, is less than epsilon. Okay. So essentially what this is saying is I'm claiming that the output of my function is getting close to that number. I can force the output to get close to that number using whatever standard you give me. Giving any standard of closeness for how close we want the output to get to L, we can force it to get that close by forcing our input to get close to p naught. Okay. All right, so that's our definition. We're going to basically use this definition once in the next video. We're going to use it to prove that a certain function is continuous. So I'll start the next video with a definition of continuity, just reminding you what that means and saying that that definition does extend to these new types of functions. And then we'll use this definition to prove that a particular function is continuous.